In this video, I'm going to talk about two new procedures in Statgraphics for analyzing failure times from repairable systems. Previous versions of Statgraphics have had several procedures: life tables, arrival analysis, Arrhenius plots, life data regression, and so forth, for analyzing life data, but they all assume that all failure times come from a single distribution. Now that may be true when an item fails if it's replaced by a new item, but if an item is repaired, then the time to failure after it's repaired may not be the same as if you've replaced the item, the failed item, with a new item. In these procedures, we're going to be interested in estimating parameters such as the mean time between failures, and to study how that mean time between failures may change the more times the item is repaired. As an example, we're going to look at some data from the classic book called The Statistical Analysis of Series of Events by Cox and Lewis. It has to do with the number of operating hours between successive failures of aircraft, of the air conditioning equipment on aircraft, and there's a sample of 13 aircraft from which data has been obtained. As I mentioned, there are two different procedures for handling data from repairable systems. The one we'll talk about is one in which the data available to us are the actual times between failures. In some cases, you don't have the actual time between failures. All you know is how many failures occurred within fixed intervals. For example, how many failures occurred each year. There's a second procedure to handle that type of data. I've loaded into the Statgraphics datasheet a file called failures.sgd. This is a sample data file that's shipped with Statgraphics version 16, so you can actually try this out for yourself. There are 13 columns in this datasheet, one for each of the 13 aircraft that we're going to look at. And what it shows is the number of operating hours on each of the aircraft every time the air conditioning equipment failed. So for example, on the first aircraft there was a failure after 194 hours, after 209 hours, after 250 hours, and so forth. This is going to be the basic data from which we want to estimate mean time between failures. To analyze the data, I'm going to go to the top menu to Describe, Life Data, and pick the Repairable Systems Times procedure. On the dialog box that comes up, I'll specify that I have the failure times of 13 aircraft and press OK. I'll be offered several different models. I'll be offered a model based upon a homogeneous Poisson process. That would be one in which we assumed a constant failure rate regardless of age. There's also a stationary renewal process. That's a process in which the failure rate is constant, but the distribution of time between failures is not exponential the way it is in a homogeneous Poisson process. The one I'm more interested in, however, is the non-homogeneous Poisson process. That's a process in which the failure rate may change. Now, there are a number of different models that I could postulate for the rate: a power function, various exponential models, an IBM model. I'll take the default in this case, which is the power function. It's going to offer me now several different tables and graphs. I will, for the moment, take the defaults and press OK, at which point an analysis window will open. The first plot I'm going to look at is in the upper right corner. This is a plot of failures of each of the 13 aircraft versus number of operating hours. It's interesting to note that some of the aircraft have been in service quite a bit longer than others. What we need to do is somehow combine all of this information into a single estimate of mean time between failures. If I put this plot away and look at the one below it, this is also a very interesting plot. What this plot shows is the cumulative number of failures for each of the 13 aircraft over time. In the middle of that, you'll see a line labeled mean. This is the estimated mean number of failures per aircraft over time. It's calculated by fitting, in this case, that power function, power curve for the non-homogeneous Poisson process. It's almost linear, which would imply a constant failure rate, but I believe I can see a little curvature upward in increasing rate as the aircraft get older. To actually see the equation for that fitted curve, I can go up to the Analysis toolbar and press the Tables and Graphs button and ask for the point process model. This will show me several models, one for the estimated rate at which failures occur, that would be in failures per hour, a second equation for the curve itself, the mean cumulative events model, and finally an equation for the mean time between failures. Now that's what I was really looking for, that equation there, mean equals. And you can see that it's a power function, 2.16 times t raised to the minus 0.129. Now that particular function, that mean, will be decreasing somewhat with t. So as I expected, the mean time between failures seems to be decreasing a little bit as the product ages, as the aircraft get older. Down below, you'll also see a goodness of fit test, a Kolmogorov-Smirnov test. Since the p-value of that test is greater than 0.05, at the 5% significance level, the model that I'm using appears to be adequate for my data. There are also some cases where you may not be happy with any of the parametric models that the procedure offers. In that case, you can go back to the cumulative failures plot. Click the right mouse button, go to Pane Options, and ask for a non-parametric estimate instead. What this will do is take the 13 traces, the 13 lines for the different aircraft, and average them. Now, it's a tricky little calculation to average them since the traces are all different lengths. But Statgraphics knows how to do it, so we'll let it worry about the calculations. Anyway, from that sort of curve, that non-parametric estimate, you can also see a little bit of upward curvature, implying an increasing failure rate with age. Finally, there's one more interesting question I can ask of this data, and that is, does a single model in fact appear to be appropriate for all 13 aircraft, or are there apparently significant differences amongst the aircraft? To test that question, I can go to the Tables and Graphs button and ask for failure rate statistics. At the bottom of this table, you'll see what's called a likelihood ratio statistic that tests whether or not there's a single model that's appropriate for all 13 aircraft. The p-value on this test is quite a bit less than 0.05, which would lead me to believe that in fact there may be significant differences amongst the aircraft. It would take some further investigation to find out exactly what was causing those differences.